All right, let's dive into some of these word problems here. So the first problem, we have an island, and we have an initial population, and we got a population after 10 years. So the initial population is 200, and after 10 years, the population is 800. So after 0 years, conveniently, the population is 200. Looks like 200 people moved onto the island. And 10 years later, they had a boatload of kids, it seems. So after 10 years, we have 800 people on the island. Okay, so let's remember our original differential equation here. We'll have, let's call this time in years, and then this is the choice is ours to make. We could call it X, we could call it whatever. I'm going to call it T for time. I'll call this P for population. So the change, dP, the change in population with respect to time, this is just how fast the population is changing with respect to time, is equal to some constant, we'll call that K, times the population. And I want you to write this down. You might be thinking, why don't I just skip to the solution that, y equals C e to the KT? I want you to write this down too, because I want you to make that connection between this ordinary differential equation and its solution. It's a very helpful thing. It's a bit hairy to solve using calculus. It's kind of annoying to solve using calculus, actually, but it's to go directly to the solution. It'll save you a lot of time later on. So I want you to kind of get that in your head there. So the solution to this differential equation would be P, population, equals some constant times E to some other constant, this K, times T. So this differential equation leads to this exponential equation, and now we can start to solve. And like I said, we'll always have initial condition of 0, and again, I'll have an exemplar on how to solve an equation where you don't have an initial condition of 0, but for now we're just going to do that. So let's see, time equals 0, so that's going to, we're going to plug a 0 in for this T. That's going to wipe all of this out, and then our P would end up being 200. So we get 200 equals C times, well, E to the K times 0 would just be 1. So C equals 200, which we already knew because this initial population was 200, but that's how you solve that. So we know that C is 200. Now all we have to do is solve for K. And we use this second set of data here. So let's see, P would be 800. So 800 equals C, which we now know is 200. 200 times E to the K times 10. Because T equals 10 in this case. Okay, let's get this E all by itself by dividing both sides by 200. 800 divided by 200 is just 4. So we get 4 equals E, we'll just call this 10K. E to the 10K. Since we have an E here, we'll take a natural log of both sides. So natural log of 4 equals the natural log of E to the 10K. These are inverses. The natural log of E to the something is just that something. And we'll leave this alone, just natural log of 4 equals 10K. And then we divide both sides by 10, so we get K equals the natural log of 4 over 10, which, whoops, I turned my computer off here, 1 second. I'm doing all this math in my head. Did you realize that? Let's see, natural log of 4 over 10 ends up being 0.1386. We'll call it 0.139. So K roughly equals 0.139. Okay, so now we know C, we know K, so we've got our full equation now. So P, the population, is going to equal C, which is 200, times E to the 0.139 T. And looks like we're asked to find what the population is going to be after 15 years. So all we'd have to do is punch in 15 for T. So it'd be 200 times e. So p would equal 200 times e to the 0.139 times 15. And this is one of the things you're just going to punch into a calculator. Let's see here. So e to the, bear with me 1 second here. It's the e to the 0.139 times 15, and all of that times 200 would be 1608.9. So we'll call it 1609. So the population when t is 15 is going to be 1,609 people. So we're really kind of getting much bigger after 10 years. We really start gaining some steam there. So that's the idea. All right. Numero 20. Wish I had a real dry erase eraser. Okay, so we've got some compounding interest going on here. We've got investment. So after 0 years, I guess our initial investment is going to be $1,000, and after 2 years, that has grown to $3,000. Not a bad account at all. I want in. Okay, so let's label these, and again, you can label these whatever you want. I'm going to call this time, T for time, and we'll call this, I'll just use $sign. That sounds like fun. I could use M for money or whatever I want, but we'll use $signs because $signs are, I'm just going to solve the dang problem. Let's just, okay, so we get the change in money, so D $sign with respect to time, so D $sign dt is equal to some constant K times the amount of money present, so K $sign. And the solution, just like it was before, is amount of money is equal to some constant C times E to this constant K times T. And it's going to get a little repetitive, but I want you to write this down and keep doing this. It's going to be a good habit, I promise you. So now we know our initial condition, and since we're kind of starting to get the hang of this, we'll just, we know if we plug 0 into here, we're going to get 1,000. So 1,000 equals this constant times 1. That's just going to collapse to 1. So we know that C equals 1,000. It's our initial condition. Okay, now that we know that C equals 1,000, let's use this other data point to figure out what K is. So let's see, we get 3,000 equals, well, C is now 1,000, so it'd be 1,000 times E to the K times 2. T is 2. So let's write that as 2K. Divide both sides by 1,000, we'll get 3 equals E to the 2K. Take the natural log of both sides. Natural log of 3 equals the natural log of E to the 2K. And again, let me write this explicitly so you can see why this ends up going away. I'll show you another way it does. So natural log of 3 equals the log base E of E to the 2K. Watch what happens here. Remember, with our log rules, if we're taking log of something and the something that's on the inside of the log is taken to an exponent, that exponent can move right down to the front. So this would be natural log of 3 equals 2K times the log base E of E. Well, E to what power equals E? Well, that's just 1, right? So that kind of goes away. So we get log of 3 equals 2K. Divide both sides by 2, we get log of 3 over 2 equals K. And what's the natural log of 3 over 2? Let's punch that into our trusty calculator here. Let's see. Log of 3 over 2 over 2 ends up being about 0.549. So K roughly equals 0.549. Okay, so now we have our C value and our K value, so we can assemble our equation. So the amount of money that you have equals 1,000 times E to the 0.549 T. That would mean that you're earning 54% interest, which is not a bad account at all. You must be some kind of defense contractor or something. So there's going to be our solution there. There's our equation. And we're asked to find at what time does the amount of money end up being 2,000. Okay, so it's going to be somewhere between 0 and 2 years. Obviously, if this was a linear equation, it would be read at 1 year. But since this is an exponential, let's see what we get here. Let's save this equation here, and I can get rid of all this work just to kind of save some room here. Okay, so we're not plugging 2,000 in for t. We're plugging 2,000 in for the money. So it's going to be 2,000 equals 1,000 e to the 0.549 t. And we're going to figure out how much time it's going to take for our money to become $2,000. Let's divide both sides by 1,000. So we're going to get 2 equals e to the 0.549 t. Take the natural log of both sides. Natural log of 2 equals natural log of e to a certain power is just going to be that power. So it'd be 0.549 t. Divide both sides by 0.549. So t would equal natural log of 2 over 0.549. Like I said, you end up in ugly numbers with this, but let's just power ahead. So let's see, over 0.549. And it's a natural log of 2 this time. So 1.263. So t would roughly equal 1.263. So after a little over 1 1/4 years, you're going to actually have $2,000 in that account. Okay. So it takes you just over a year to double your money. Not a bad account at all. I want in on that. All right, our last question. Okay, so we've caught a certain bacteria, and we're measuring its how many bacteria are growing inside us. I'm not sure why we're taking an antibiotic to get rid of the bacteria, but I guess we're sacrificing our body for science here. At our initial condition, 0, so after 0 minutes, there are 40,000 bacteria. And after 30 minutes, after a half hour, that's multiplied by 10. We have 400,000. Okay, so we'll call this T for time, that's fun, and we'll call this B for bacteria. So the amount of bacteria, the change in the amount of bacteria with respect to time, so dB dt, the amount the bacteria is changing with respect to time, is equal to some constant, K, times B. And the solution to this differential equation is B equals some other constant, C, times E to the KT. Okay, so let's figure out what our C value is. And we've done this a million times. As long as we have this 0 here, that's a very convenient thing. Our C is going to end up being that B value that's associated with the 0 time. So we already know that C equals 40,000. And if you're not sure how I got that, either go back to one of the other solutions or ask me when I get back. We'll go over that just to make sure we get that under belts there. But C equals 40,000. So now we can use this second equation to figure out what our K value is. So 400,000 equals C, which is 40,000, times E to the K times 30. So 30 minutes later, this thing's growing like crazy. Okay, so we can divide both sides by 40,000. 400,000 divided by 40,000 is just 10, so that makes things a little more simple. 10 equals E to the, we'll call that 30K. Take the natural log of both sides. Natural log of 10 equals natural log of E to the something is just that something, so it equals 30K. Then divide both sides by 30, so we get the natural log of 10 over 30 equals K. And the natural log of 10 over 30 is 0.07, we're at 0.0767, so we'll call it like maybe 0.077. So that roughly equals 0.077. So we just plug in our C and K values, so we get B equals 40,000 times E to the 0.077 T. And we're asked what happens after an hour. Well, an hour is 60 minutes, so we can plug in 60 for T. So it'd be B equals 40,000 times E to the 0.077 times 60. And let me just punch that in real quick. This is just, busy work calculator stuff. So let's see, we'll go, let's see, 40,000 times E to the 0.077 times 60. And we have 4,059,761 roughly. So B in this case will roughly equal 4059761. 4059761. So let's see, 4,059,761 bacteria are in your body after an hour. So you might want to go see a doctor about that, because after 1 hour it's multiplied itself by a factor of 100, it looks like. So yeah, you're going to want to get that checked out. All right, hope this was helpful, and I will see you hopefully on Thursday. Take care, guys.